Hi, it's Mr. T here. In this video we're going to go over the important reactions of alkanes and alkenes. Now I have over 20 years of experience teaching high school chemistry, and I have specific insights that I want to share with you so you can do well in this subject. If you really want to master the understanding of organic chemistry, then this video is a must watch. So in particular, if you're doing level 2 NCEA, this video follows a course of videos that I have set. Just click on the link above to go to the playlist of all the so you can access all the other videos. Right. What is your understanding of organic chemistry before this video? Click on the poll above and let me know. Is it anything like the two individuals on the left? Right, let's have a look at the reactions of alkanes. So what I've done here is I'm going to draw a wee map for a start of the general reactions that alkanes undergo. And actually the first thing I'm going to show here is that crude oil, that's the oil that you pump out of the ground, actually contains a lot of alkanes. And they can be separated by a process called fractional distillation. Basically, you construct big steel columns, like as big as buildings, and you heat up the crude oil, and you have pipes at different heights along. The pipes at the bottom bring out the really thick bitumen that goes on roads, and the pipes at the top bring out the gas, and in between you get petrol and diesel. And anyway, that's where you get your alkanes from. But what are the reactions of alkanes? There's two reactions we can look at specifically. The first one is cracking. And this is where we make alkenes from alkanes. And the second one is a substitution reaction where bromine replaces a hydrogen. So let's look more closely at these two reactions. So cracking paraffin. We can actually do this in the lab, in the class, and it's often done in many science labs around the country, around the world. What you do is you take a test tube, a boiling tube, a bigger tube, you fill it with paraffin and you put in there some glass wool. Now the glass wool is important because the silicon dioxide acts as a catalyst for this reaction. So you heat up this glass tube and this will produce bubbles coming off the paraffin. Now paraffin is a thick alkane, so it's maybe about 20 carbons long, and what it does is it produces bubbles. You can collect that's ethane gas, and you can test it to see if it's an alkene. Just if you ever do this, take care, because if you don't have a valve in your pipe, sometimes if you take the heat away, the paraffin cools down, the air cools down, the water goes back into the tube and boom, explodes because of the hot glass. Anyway, that's how we produce alkene in the lab. There's a process called cracking, and basically what we do is we take the alkane and we heat it. When we heat it, we split off sections of the alkane, and when those sections split off, they make the alkene. They also make another alkane, which again can go and get split. So we can use this cracking process to make smaller alkanes, and it's important if you have like lots of long chain alkanes, like 20 carbons long, because you can split it up to make 8 chain carbons, which is what you have in petrol, which is octane. Okay, so you have a selection of different octanes in petrol, or one's about 8. So this cracking is used to create smaller alkanes and also alkenes, and that's the process of cracking. Okay, so another reaction that alkanes undergo is a bromine water test. We can react them with bromine water. So we have a test that we do in class. We take a sample of alkanes, we put some bromine water in, we get a wee orange color happening there, and then what we do is we shake it. Now after shaking it, nothing happens, so we take our tube and we go and sit it by the window in the sunlight getting UV light for 50 minutes, and lo and behold, the orange color disappears. Now the orange color comes from aqueous bromine. Br2 has an orange color, so it has disappeared. Where has it gone? Well, it's undergone a substitution reaction. What a substitution reaction is, when we take one atom and we substitute it with another atom. So we take the hydrogen at the top left of the alkane and we replace it with a bromine. That is a substitution reaction. Notice we also produce some hydrogen bromide as another product in this reaction. So that's the two reactions for alkanes. We've got the cracking and the adding of bromine, or the substitution reaction with bromine. Okay, so alkenes have a whole bunch of reactions that they undergo, and they're usually all the same type of reaction. And it's to do with the double bond that's in the middle of an alkene. An alkene has a double bond between two carbons. What can happen is one of the bonds that make up the double bond can break, and then each carbon can form a separate bond to another molecule or atom. Now, because that makes a variety of different addition reactions. We've got the addition to make an alkane, an addition of hydrogen. We've got the addition of water to make an alcohol. We can add halogens to make haloalkanes, or we can just add them all together in a big long chain and we can produce polymers that are plastics. Now, we can also undergo an oxidation reaction where we can have an oxidation reaction with permanganate, and we can produce something called a diol. Now, this slide here, or this picture that we see at the moment, is a really good summary of all of the reactions that alkenes can undergo. And I've put on to this part of the video right here. If you pause the video, you can see all of the reagents that are needed to go from an alkene to its end product. You can also see the type of reaction. So just pause the video and write this down if you need it for study. We can also have, and we're not going to look at this in alkenes, but many of these products that are produced can also have another reaction that goes backwards. Okay, so before we start looking specifically at the reactions of alkenes, do you remember how to name them? So here's one here. How would you name this? So how I would do it is, first I'd notice that there was a double bond there at the end, and that there were 5 carbons in the longest chain. So this is going to have the double bond off carbon number 1, and it's going to be pent 1-ene. Okay, the first type of reaction we're going to look at is hydrogenation. Now, with hydrogenation, what happens is we take an alkene and we add hydrogen to it in the presence of a catalyst. In this case, it's platinum. The catalyst you can also use is nickel. So sometimes over the arrow you write H2/Ni, or it's written that. Either one of them is perfectly fine if you're writing down how to carry out this reaction. Because we're adding just hydrogen, so the double bond is breaking on either side. Well, one of the bonds is breaking on either side of the double bond. We've got the 2 carbons making 2 new hydrogens. And that produces an alkane. So that's hydrogenation. Next type of addition reaction, these are all addition reactions, is hydration. Now, hydration is the addition of water. Notice again, we've got an alkene here because of the double bond. Now remember what's going to happen. That double bond, one of the bonds will break, and then new things will form at the top and the bottom. Now what we're really adding here is water in the presence of concentrated sulfuric acid, and water gets split into both a hydroxide and a hydrogen. So a hydrogen gets added to one side and a hydroxyl group gets added to the other. So therefore, what happens here is when they undergo addition reactions, they can break the double bond and form 2 new attachments. Okay, so alkenes undergo reactions with halogens, and one of the important halogen reactions is the test with bromine water. So we saw the test with bromine water for alkanes, where the bromine water stayed orange and we had to put it in sunlight for 30 minutes for it to change color. Well, when we take a sample of alkene and we add our bromine water, it goes orange, but as soon as we shake it, it changes color straight away. Now, when I say straight away, it's going to be within 5 seconds. Now, that straight away color change is a definitive test for an alkene or possibly an alkyne. It's a test for unsaturated compounds. Now this is called halogenation, but again, it is just an addition reaction. So if you were to be asked what type of reaction this was, you could write addition or you could write halogenation. So what's happening here is the double bond is breaking, but because we're adding Br2, we have a bromine to add to either side, so we get 2 bromine functional groups added. So it would be, this one here would be 2,3-dibromo. So we can also undergo halogenation by adding to the alkene by adding the halogen with a hydrogen. So with any of these halogenation ones, with the Br2 above, it could be Cl2, it could be F2, it could be I2, and down the bottom you could have HBr or HI or HF. So what happens is when we've got that, a hydrogen goes to one side and the chlorine goes to the other. Now notice just on the bottom here is a word called major. We're going to talk about that later. But if you look at that, you might think that what side would the chlorine go to? Well, the side that it goes to the majority of the time is to the left-hand side or off the second carbon. Okay, so this is the last type of addition reaction, and it's called polymerization. In this reaction, we make what are called addition polymers. Now, addition polymers happen when we have an alkene, we have multiple alkene molecules, so thousands of them. They're all identical here, and what's going to happen is one of the bonds in the double bond breaks, and now we get an atom or a molecule joined to the blue carbon and one to the red carbon. Now notice on the red carbon at the moment there's a chlorine attached, so we can see that when the actual molecule goes to attach to other similar molecules, the chlorine moves up to the top, the hydrogen to the bottom here, this hydrogen to the top, this hydrogen to the bottom, and then it attaches to the next one. And because of that, we get these lovely repeating patterns. So you can see the chlorine and the hydrogen from the red carbon on the left, and the hydrogen and the hydrogen off the blue carbon on the right here. Now, when we write or draw these reactions, we always put 3 of these repeating units or this pattern in to show that you know what you're doing. And the end is just a wee squiggly line to show that this keeps continuing on, and it goes on for thousands of atoms. Now, to carry out this reaction, you put it under heat and pressure. So what we've done is we've taken an alkene, now we've made a polymer. This specific polymer here is PVC, polyvinyl chloride, vinyl being the old name for ethene, vinyl. So polyvinyl, or lots of ethene chloride, because poly means lots of. Okay, here's another reaction that makes another polymer. So in this case, you can see that it is the blue carbon that has something different coming off it. Now, if we actually push these atoms or groups at the end, if we push them up vertical and we push these ones on the right vertical, and then we join them to the next molecule, or to the next atom of the next molecule, we can get this repeating series. But you can see at the bottom here there was a CH3 group, so this was actually a propene here. And so now what we get is lots of propenes have been added together, and they've been added at the carbons that have the double bond. So you have to push the CH3 down out of the way. So we've started with this alkene called propene, and now we've made this polymer called polypropene or polypropylene. So it's the type of material that you use in thermal clothes. So you might have long johns when you go out hunting or tramping or something like that, made of polypropylene. It's also used as a universal plastic that to help. I guess you use it in building. So polymers often have these chains of thousands long, so it makes big long strands. So you get these big long strands all sort of mixed up together. You get lots of multiple of these long strands of thousands of these. They're very, very small, but because of that, it gives them that they're able to be they have a plasticity to them. That means that you can shape them. So when you heat them up, you can change their shape or mold them, and when they cool down, they go solid again. And you can reheat them again and do that. And the plasticity is where these polymers get their name from, because really they're just plastics. PVC, common plastic that you find in all around your house. The floor on your kitchen is made of PVC. Your spouting in your house is made of PVC. The pen in your hand is made of PVC. As I said, polypropylene, that's used a lot as well. So that's addition polymerization. So, do you understand how the reactions we've talked about might work? How are you up with that? Well, if you want to see that you understand what we've been doing here, can you work out what the answers to these reactions are? What are the products produced in these reactions? Can you give the name of the products, and can you also give the name of the type of reaction? So if you want to go ahead and do that, just pause the video, write them down, and see if you can work it out yourself. I'm going to keep going, and I'm going to show you the answer now. If you haven't paused, well, just watch and see what the answer is. So first one, platinum and hydrogen. I've actually got that around the wrong way. It doesn't matter what way we put it. So what's going to happen is we're going to add the hydrogen, and we get this molecule here. We've gone from an alkene to an alkane, and this is butane. Of course, it's an addition reaction. The next one, we're adding water. So we're going to add an H to one side and an OH to the other. In this case, I've produced pentan 3-ol. Guess what? This is an addition reaction as well. The third one, we're adding bromine. So that's right, Br2, you're going to add a Br to either side where the double bond was, and you're going to get 1,2-dibromohexane. The last one, we're adding concentrated hydrochloric acid. Sometimes you'll see in some study guides that they'll just say hydrochloric acid. Guess what? It's concentrated when you do it, so you're never going to get it wrong for putting concentrated in front of it. An H is going to go one side and a Cl on the other. There you go. 1-chlorohexane. How many of those did you get right? Oh, sorry, forgot to say, it's an addition reaction as well, because they're alkenes. They undergo addition reactions. That is their thing. That's how you know. Okay, so sometimes when we do addition, we're adding to asymmetric alkenes, and it produces two different products. Before we can work out whether this occurs or not, we have to better identify what type of alkene is asymmetric. So a technique that I use for identifying whether something is symmetric or asymmetric is I take the molecule, okay, and I put an X in the middle of it. And then what I do is I do in my mind a 180-degree rotation. And if the 180-degree rotation, boom, done, fits in the same place than it was originally, then that molecule is a symmetric molecule. If I put the X on and I do the 180-degree rotation and it doesn't fit in the same space, it's an asymmetric molecule. Now, if we have an asymmetric molecule, what can happen is whenever we add water, H2O, or HEX, that's hydrogen chloride, hydrogen bromide, hydrogen iodide, or hydrogen bromide, the hydrogen and the hydrogen that's always produced, or the OH for water, or the halogen for the other one, has two different choices on where they might be put. Now, let's have a look at this. I've got hydrochloric acid here, and I want to add it to my symmetric molecule. So this is butyrene. So I'm going to add an H to one. See, I'm going to add the H to the left and the chlorine to the right. And I'm going to do the same. I'm going to flip it around. I'm going to put the chlorine to the left and the hydrogen to the right. What you might notice is actually those are the two possibilities, but they're both 2-chlorobutane. They're just the same atom, just flipped or turned 180 degrees. So if I have a symmetric molecule and I add hydrogen chloride or water or another type of molecule like that, then we are going to get the same product produced. However, that's not true when we have an asymmetric molecule. So have a look at the bottom here. This is asymmetric because remember, if I put a cross here and turned it around, it wouldn't, after it's turned around 180 degrees, it wouldn't superimpose on top of itself. So when I add the hydrogen chloride, I put the hydrogen on the left side here and the chlorine on the right. And then on this one, I put the chlorine on the left and the hydrogen on the right. When I go to name these, or even if you look at them, you can see they're two different molecules now, because one has the chlorine on the second carbon, 2-chlorobutane, and one has the chlorine on the first carbon, 1-chlorobutane. Now, it so happens here that, okay, so Markovnikov came up with a rule to tell us which one of these products is more likely to be made. So we use, when we do that, the product that's more likely to be made is called the major product. Now what actually happens whenever you have an alkene, right? And you've got, say, a test tube, or you've got a beaker, or even if you've got a bucket of alkene, you've got trillions and trillions and trillions of molecules in there. Now, you have the potential to make both versions of the product. Okay, you can make the 1-chlorobutane or the 2-chlorobutane, but one of them actually is more likely to happen, and we get it the majority of the time, and that's called the major product. Now, Markovnikov had a rule for us to remember which one is going to be the major product. Now, to do that, he made this little statement that said the rich get richer. Now, you have to, what he was implying then is people have money, they get more money. In this case, the money is the hydrogens. So the carbon that has the most hydrogens directly bonded to it gets the hydrogen bonded to it, the new one. It's rich, it gets richer. The halogen attaches to the other carbon. So if you look at it here, you can see that on the left, the red carbon is the rich one, right? So where's the hydrogen going to go? It's going to go to the rich carbon, and now that carbon's going to have 3 hydrogens the majority of the time in this reaction. Let's say, for instance, that 80% of the time, the hydrogen goes to the rich place. But sometimes we will get the other product made, and 20% of the time, we get the minor product made. That's the OH goes to the rich place. Now, what that means is anytime we undergo this type of reaction, a water or a halogen hydride, or no, it would be a hydrogen halide. Okay, anytime that we add that to an asymmetric alkene, we're going to get 2 different products, but we now know, using Markovnikov's rule, which one is going to be the major product. Okay, so the last reaction we're going to look at is the reaction of an alkene with permanganate. Now, we can use the permanganate to do an identification test for alkenes. So if we're taking a sample and we're not sure whether it's an alkene or not, let's say we had an alkene and alcohol, and we wanted to, well, let's say if we had an alkene and an alkane, or an alkene and a ketone, or an alkene and a carboxylic acid, and we wanted to find out whether it was actually an alkene, we add 10 drops of permanganate solution to it. Permanganate solution is purple. We add the 10 drops, we give it a shake, and it goes brown. So that's almost in 10 seconds it'll go brown, right? So that's the distinguishing test for an alkene. So notice, remember that this is the permanganate test to see if something's an alkene, or possibly it could be an alkyne. Remember, it's just a test for unsaturation. But also that we had the bromine water test that we could use as well. It just depends what's available. They both work. Okay, so this is an oxidation reaction. What's happening here is the purple permanganate is being reduced to the brown manganese dioxide, and in the process it oxidizes the alcohol to what's called it oxidizes the alkene to an alcohol, and the alcohol it oxidizes it to is called a diol, or sometimes called an alkanediol, but I just like to call it a diol. So that's the last of the tests for the alkene. So we've gone over the 5 most common reactions that alkenes undergo. And what I'm going to do here is right in the middle of this screen, here is an alkene, so it's pent-2-ene, and I've drawn 5 arrows coming off all around it. So we've got 5 different reagents that correspond to 5 of those different reactions that we've looked at. So what I'd like you to do is just pause the video and write down this scheme here. So write down the molecule in the middle and the arrows with the reagents. Once you've done that, I'd like you then to write the products that are produced from each of those arrows, or the answers. And also underneath the reagent, just write down what type of reaction it is. So what we want is the product for each of the reaction and the type of reagent. Once you've finished that, unpause the video again and I'll go through the answers. Okay, so you've unpaused the video, and the answer to adding hydrogen with a platinum catalyst is we get an alkane, pentane. And of course, this is an addition reaction because we've added things to the bond that's broken from the double bond. The next one we're going to look at is permanganate, MnO4-. We might remember that when we added that, we get a diol. And in this case, we're going to get pentan 2,3-diol. This, of course, we're adding oxygens across the double bond, is oxidation. So the third one here is a bit of a trick, and I should have told you this before we started. But if you look at the molecule in the middle, it's asymmetric. And we're adding water, which means we're adding a hydrogen to one side and an OH in the other. Now what that means is we're going to get the answer of pentan 2-ol half of the time, but half of you would have got the answer pentan 3-ol. Or if you're really switched on, you would have written both, because those are both the products that you would get if you underwent this reaction. We don't know which one is the major because we can't use Markovnikov's rule, because the carbons for a start both had 1 hydrogen each. This is an addition reaction. So again, with with adding the concentrated hydrochloric acid, we had 2 possible answers here. I've only drawn 1. The other possible answer is 2-chloropentane. The last reaction here is when we take this molecule. Now remember what we had to do, we're under heat and pressure, so we have nothing else added to it. It's going to react with itself, it's going to undergo polymerization. So you're thinking the left-hand carbon, the whole group is going to push down, so that group of 2 carbons and hydrogens, the ethyl group, is going to push to the bottom, and the carbon on the right of the double bond, the methyl group, is going to push to the top. So what we're going to get is a polymer that looks like this. And I guess if you had to name that, it would be polypentane or pentene or something like that. So this is an addition reaction, and so was the one previous. Notice just about all of the reactions that alkenes undergo are addition reactions. So last question is, has this helped? Is there any help to this? Click on the poll above and let me know. Can you understand some reactions better now than you did beforehand? Would you be observant enough to notice the polar bear on the iceberg? So if this video was helped and you like the content of this, like, share and subscribe. You can find out other videos that I've done on organic chemistry on my YouTube site. There's a playlist for Year 12 chemistry if you want to go over that. Okay, cheers.